Welcome back to the deep dive. Today, we're really getting into the guts of electricity, into something fundamental.
Absolutely. We're talking about capacitors and those crucial insulating materials inside them, dielectrics.
Right? They're everywhere, phones, computers, you name it. And these dielectrics, they massively boost how much charge a capacitor can hold.
And our mission, really, for this deep dive is to figure out why. How does sticking this stuff into an electric field change things so much?
Yeah, how do we connect that number we measure, the dielectric constant, kappa?
The macroscopic property.
How do we connect that back to what the individual atoms and molecules are actually doing, wiggling around, stretching?
Exactly. It all comes down to the molecules. And fundamentally, you've got two basic kinds to think about.
Okay, lay them out for us.
Well, first, you have what we call nonpolar molecules. Think simple symmetrical things. Oxygen gas, O2, or maybe a helium atom.
Symmetrical, meaning the positive and negative charges are, perfectly balanced. Centered.
Precisely. They sit right on top of each other, electrically speaking. So no natural electrical lean, no built-in dipole moment, at least not until a field shows up.
Okay, nonpolar. Got it. What's the other type?
Then you get the more interesting ones, the polar molecules. Water is the textbook case, H2O.
Water, right. It's kind of bent, isn't it? Not symmetrical.
Exactly, that bend is key. The positive and negative charge centers don't line up. So even with no external field, they have this permanent built-in electrical bias, a permanent dipole moment, we call it P0.
So they're always a little bit electrically lopsided, ready to react.
Ready to react, that's a good way to put it.
Okay, let's tackle the simple case first then, the nonpolar atoms. What happens when you stick, say, a helium atom in an electric field? This is electronic polarization, right?
That's the one. It's pretty intuitive, actually. The electric field, E, pushes the positive nucleus one way, and it pulls the negatively charged electron cloud the other way.
So the whole atom stretches out slightly.
Yeah, like a tiny, tiny balloon being pulled at opposite ends. It wasn't a dipole before, but this stretching creates one, temporarily, an induced dipole moment.
How do we model that? How did physicists first think about it?
Well, the classical model, which is surprisingly effective, treats it almost like a little spring system. Imagine the positive nucleus tied to the electron cloud by an invisible spring.
Oh.
The external field, E, pulls on the charges, stretching the spring, but the atom's internal structure pulls back, trying to restore the original shape. Like a simple harmonic oscillator, if you remember that from basic physics.
Right, Hooke's law kind of thing. Force is proportional to displacement.
Exactly. And since the electric force is Q times E, and the restoring force is proportional to the displacement, say X.
Then the displacement X must be proportional to the electric field E.
You got it. And if the displacement is proportional to E, then the induced dipole moment, P, which depends directly on that displacement. Well, P is also proportional to E.
Okay, so P equals some constant times E?
Precisely. We write it as P equals alpha times E, or more accurately, E local, the field at the atom. And that constant alpha, that's the key here. It's called the atomic polarizability.
Alpha. So that measures how easily the atom stretches, how squishy its electron cloud is.
That's a great way to think about it, how floppy or squishy the electron cloud is. And here's the kicker. Using this very simple classical spring model, you can actually calculate a predicted value for the dielectric constant, kappa, for nonpolar gases like hydrogen.
And does it work?
It works remarkably well. I mean, it's not perfect. Quantum mechanics gives a slightly better number, but for such a simple model, it gets surprisingly close to the experimental measurements. It really shows that this macroscopic kappa value comes right out of this basic atomic stretching.
Okay, stretching nonpolar atoms, check. But now for the other kind, the polar molecules, like water, they already have a dipole moment. What happens there?
Yeah.
This is orientation polarization.
Yes, and it's a whole different ballgame because
Yeah.
they have that permanent dipole moment, P0, just sitting there.
So if there's no external field, what are they doing? Just pointing randomly?
Exactly. Thermal energy, heat keeps them constantly tumbling and rotating, billions of them, all pointing in random directions. So on average, the net polarization is 0. Nothing adds up.
Right. Like dancers just milling about randomly on a dance floor.
Perfect analogy. But then you switch on the external electric field, E.
Okay, now what? Does it just snap them all into alignment?
It tries. The field exerts a torque on each dipole, trying to twist it so it lines up parallel with the field. That's the lowest energy state for the dipole. When it's aligned, potential energy, U equals minus P0E cosine theta.
But you said thermal energy is still there.
Exactly. You have a fight going on. The electric field is trying to impose order, line everyone up, but the thermal energy, KT, is fighting back, trying to keep things random and disordered. The dancers want to keep moving randomly.
So it's a competition between the field's ordering effect
Yeah.
and the heat's randomizing effect.
Precisely. And who wins depends on the temperature.
So you don't get perfect alignment.
Almost never. Not at normal temperatures. You only get partial alignment. The stronger the field, the better the alignment. But the higher the temperature, the worse the alignment, because the thermal chaos wins out more often.
Okay, that makes sense. If the dance floor is really hot and energetic, it's hard to get everyone facing the same way.
You nailed it. And when you work through the statistics of this, using statistical mechanics, Boltzmann factors, all that stuff, you find a really crucial result.
Which is?
The average alignment, the net polarization P you get, is proportional to the electric field E, just like before. But it's also inversely proportional to the absolute temperature T.
So P is proportional to E over T.
Exactly. P is proportional to ET. This is really important. It means the dielectric effect from these polar molecules gets weaker as you heat things up.
That inverse relationship with temperature, that's the signature.
That's the dead giveaway for orientation polarization involving permanent dipoles. It leads to something called Curie's law for dielectrics. Kappa minus 1 is proportional to 1 over T. If you plot kappa versus 1T, you often see a nice straight line showing kappa dropping as T goes up.
Okay, so we have stretching for nonpolar and this temperature-dependent alignment for polar. But hang on, all this assumes the molecule is just sitting there in the external field E, right? Like in a really dilute gas.
Yes. Good point. We've only really considered isolated molecules or ones very far apart.
What happens when they're packed tightly together, like in a liquid or a solid? Does the field one molecule feels change because of its neighbors? This is the internal field problem, isn't it?
It is indeed, and it's a major hurdle. The field that any single molecule actually experiences, the thing driving its polarization, isn't just the nice average macroscopic field E that you might measure from outside.
Why not? What else is there?
Well, think about it. Each molecule creates its own little electric field because it gets polarized. And that field affects its neighbors. And their fields affect the original molecule back. It's a complex interaction.
So the actual field acting on the molecule, the eutexyl is different from the average E.
Yes, significantly different potentially. To calculate the total polarization P, which is what determines kappa, you need to sum up the effects on all the molecules, and for that, you need to know this true E-tex.
Right, so how on earth do you figure out E-tex local when it's surrounded by zillions of other interacting dipoles? Sounds impossible.
It was a major puzzle. The breakthrough came from a clever thought experiment. Physicists imagined, conceptually, carving out little cavities inside the dielectric material around the molecule they were interested in.
Cavities, like little holes.
Exactly. And they asked, what's the field inside different shaped holes? If you imagine a long, skinny, needle-shaped hole parallel to the main field E, the field inside turns out to be just B, the external field. But if you imagine a wide, flat, coin-shaped slot perpendicular to E, the field inside is different. It's actually dilo dollar epsilon dollars, which is E plus the polarization P over epsilon naught. But the crucial insight came from imagining a small spherical hole carved around the atom.
A sphere. Why a sphere?
Because it's symmetrical, and it turns out the field inside that sphere gives the best average representation of the field acting on the molecule at the center. And calculating that field involves considering the average field E plus the contribution from the polarized material just outside the sphere.
And what's the result? What is E-tex local?
The calculation shows that for this spherical model, E-tex local is equal to the average field E plus the polarization P divided by 3 times epsilon naught. So E-tex local E plus P3 epsilon.
Okay, so it's the average field plus this extra bit from the neighbors.
Exactly. That P3 epsilon term accounts for the influence of the nearby polarized molecules. It's like they add a little extra push.
So now you take this local field and plug it back into the equations we had before, relating polarization P to the field.
You got it. You substitute this expression for A-tex local back into the relationship between the polarization per molecule, which involves alpha, and the field causing it.
And what pops up?
After a bit of algebra, you arrive at a really famous and powerful result. The Clausius-Mossotti equation.
I've heard of that one. What does it look like?
It relates the macroscopic kappa to the microscopic properties. It says kappa 1 divided by kappa plus 2 equals the number density of molecules N times the polarizability alpha divided by 3 times epsilon naught.
Kappa 1, kappa plus 2, and alpha 3 epsilon. Wow.
Yeah, and look what it does. On the left, you have kappa, the thing you can easily measure for the bulk material. On the right, you have N, how many molecules there are per unit volume, and alpha, that fundamental measure of how much an individual molecule stretches or aligns.
It bridges the gap. Microscopic properties predicting a macroscopic constant.
Precisely. It's a theoretical triumph. And it works remarkably well, especially for nonpolar substances, connecting their behavior as gases, low N, to liquids, high N. Think about something like carbon disulfide text 232. This equation handles the transition beautifully.
Okay, that's huge. What about solids? We've talked gases, liquids. Solid dielectrics are obviously critical for electronics.
Right. The same basic ideas apply, but solids can have more complex structures and interactions. You even get materials called electrets.
Electrets?
Yeah, they're like the electrical equivalent of permanent magnets. They're solids that can hold a permanent electric polarization even after you turn off the external field. They remember the field.
Huh. But there's an even more extreme case, isn't there? Something called ferroelectricity.
Ah, yes, ferroelectricity. Now we're getting into really fascinating territory. The classic example is a material called barium titanate. Text barium titanate.
Okay, what's special about it?
It's ferroelectric. This means it doesn't just get polarized by a field, it has a large, spontaneous polarization built right into its crystal structure below a certain temperature. And crucially, you can flip this built-in polarization direction back and forth by applying a strong enough external electric field.
Flip it, like reversing the north and south poles of a magnet.
Exactly analogous to ferromagnetism, hence the name ferroelectricity.
And I've heard the dielectric constant for these materials can be, well, enormous.
Oh, absolutely staggering. For barium titanate, kappa can be huge, sometimes exceeding 50,000 near its critical temperature. Compare that to, maybe 2 or 3 for simple plastics, or around 80 for water.
50,000? How is that even possible? And you mentioned a critical temperature.
Yeah, the behavior is incredibly sensitive to temperature. There's a specific point, the Curie temperature, 2 Fig, where the ferroelectric property suddenly appears or disappears, and kappa spikes dramatically around that point.
So what's the mechanism? How does text BATI at A3 get this giant kappa and spontaneous polarization? Is it still about local fields?
It absolutely comes back to the local field idea, but pushed to an extreme. In the text BATI 3 crystal structure, the little titanium ion in the center is slightly offset, creating a significant dipole.
Okay.
Now think back to Clausius-Mossotti and that E plus P3 epsilon formula. That P3 epsilon dollar term represents the field from the neighbors reinforcing the polarization.
Right, this self-reinforcing push.
In materials like barium titanate, this reinforcement factor, which depends on an alpha 3 epsilon, gets very, very large. So large, in fact, that it approaches a critical point.
The tipping point.
Exactly. If null epsilon gets close to 1, the denominator in one form of the Clausius-Mossotti relation approaches 0, meaning kappa blows up. The local field becomes so strong that it can sustain a large polarization even without an external E field. The dipoles essentially lock each other into alignment.
Wow. So the material spontaneously polarizes itself because the neighbor's fields are so reinforcing.
That's the essence of it. It's a collective phenomenon. The displacement of the titanium ion creates a strong local field, which aligns its neighbors, which creates an even stronger field back on the original ion. It runs away and locks in. This also explains the strong temperature dependence near tile-layers, often described by the Curie-Weiss law, which is related to Curie's law we discussed earlier. It gets even more complex with things like anti-ferroelectric arrangements, but the core idea is this powerful local field feedback.
Okay, let's try to wrap this up. We've gone from single atoms to these wildly complex crystals. What are the main threads here?
Well, we saw that the macroscopic dielectric constant, kappa, really boils down to just 2 main microscopic mechanisms.
Right. First was the simple stretching of electron clouds in any atom when a field is applied. That's electronic polarization.
Mm-hmm. Pretty fast, happens in everything, and mostly independent of temperature.
And second, for molecules that already have a permanent dipole moment, like water, there's the alignment effect. Orientation polarization.
And that one is a battle between the aligning field and the randomizing heat. So it's very temperature dependent, decreasing as temperature goes up, following that 1/T relationship.
And the key to understanding how these combine in dense materials was figuring out the local electric field.
Absolutely. That concept of the local field 1 plus P3 epsilon 0 in the simple model is the bridge. It explains how neighboring molecules influence each other, leading to things like the Clausius-Mossotti relation.
And ultimately, how extreme reinforcement can lead to the huge kappa values and spontaneous polarization in ferroelectrics like barium titanate.
It's a beautiful illustration, really, starting with simple forces on electrons and nuclei, building up through statistical effects of temperature, and then incorporating the collective interactions via the local field to explain these dramatic, technologically important material properties.
It really is. Which leads to a final thought, maybe. We mentioned early on that even for simple hydrogen gas, the classical spring model wasn't quite perfect, and quantum mechanics gave a slightly better answer for alpha.
True. It's always an approximation at some level.
So if even that simple case has quantum subtleties, how much harder must it be to accurately model, say, really complex biological molecules? Things like proteins embedded in the electric fields inside a living cell membrane, where the shapes are definitely not simple spheres and the quantum effects might be much more significant.
That's precisely where the cutting edge of research is now. Modeling those complex environments where the local field is influenced by irregular shapes, water molecules, ions, and quantum mechanics, it's vastly more challenging. The simple models give us the foundation, but reality is, as always, wonderfully complex.
Something for us and you to think about further. Thanks for joining us on this deep dive into the world inside dielectrics.